Okay. So our next speaker this afternoon is Reimundo Heluani. Reimundo earned his PhD from MIT in 2006 under the guidance of Victor Katz, and he was then a Miller postdoctoral fellow at Berkeley for a few years before joining us at IMPA in 2010. So Reimundo will tell us about factorization.
Thank you. I'm honored and humbled to be here speaking. Thank you for the invitation. It's a pleasure to give a talk here in a place that I'm glad I can call home. I'll spend essentially all of the talk just giving intuition as to what are the objects that we work with. They're fairly abstract, but there's some structure that is emergent, that is there in several objects that I think many might be familiar with. And it's essentially going to be content-free, but I want to sell one result because I would rather sell the result of my collaborator. So if I say something new, it's going to be something that we proved with another professor at IMPA that hasn't started yet. So I would say that he's this latest acquisition of IMPA, which is Jethro Van Ekeren. All right. So the driving intuition is going to come from physics, and is this notion of locality. That I'm going to be very, very loose and hand wavy, and as the talk progresses, it's going to become technical eventually. But let's say that we have something that we call space-time, and whatever that thing is, it has a line that we call time. And if you pick a transversal slice to that thing, I'll call that space. And if you make measurements at two different points at the same time, those measurements are supposed to be independent. The result of one experiment at one point should not depend on the result of, nor influence the result of an experiment on a different point. And I want to have some sort of mathematical object that models that. And related to this, something that is probably easier to try to model mathematically is this notion that if I perform an experiment in nearby points, then the results also should be similar somehow. So this is something that, yeah, I guess in this audience that might not be the case. So several people here are experts in chaos. Well, I don't want to get into details of like dynamical systems. I might be yelled at. But this is something that I would want to model. And in particular, this puts in positions of what are the things that we might call space. Because now I need to have at least the notion of 2 points being close by. So I want to keep it in this language that you can pick for space whatever you want, but now you will need at least a topology so that you talk about 2 points being close by, or you might need a metric to talk about distance between points, whatever it is. And also, to say that two measurements are going to be similar, the space of those outcomes, or the space of the measurements also needs to have some sort of notion on when two things, so that you can compare two things to be similar. So this last notion is very simple to model mathematically. So here, this x is this transversal slice that I was calling space. And this little point x is one of those 2 points that were x and y. And in order to talk about the possible outcomes of these measurements to be similar, to vary continuously or to vary smoothly, you're going to talk about fibrations in whatever category you're feeling. So if you want to have your x to be, say you're a differential geometer, and you want to have x to be a differentiable manifold, then you will require that the space of all possible measurements over all possible points is a nice, smooth manifold. And this vertical arrow, you're going to consider it to be a submersion, for example. If you're an algebraic geometer, you're going to think of varieties and a flat family of varieties for that map. Whatever your preferred word is, the fiber at the point is what I was considering as the outcomes of an experiment at the point x. And this fiber is supposed to change smoothly. If it's the fiber of a submersive map, you're going to have, for example, constant local triviality, constant dimension, whatever it is. But this is the very first notion, the very first invariant that we want, that the dimension along the fiber should be constant, or locally constant at least. But I talked about measurements at different points. So I not only need a fibration over x, but I need a fibration over x squared, because I want to make experiments at x and y. So instead of thinking of 2 points on x, I can think of 1 point on x squared, and I still am going to have a fibration over x squared. And Well, same picture as I had in the previous slide. So now, of course, these two fibrations, these two bundles cannot be independent. And remember, when I talked about locality, I said this experiment should be carried in two different points, not the same point. So let's take on x squared this diagonal. That's the red line there. And I'll follow this vibration of which I called y2 that was over x squared. There are some special points that lie over the diagonal. I'm not allowed to perform two different experiments at the same point. So that's a compatibility between the vibration over x and the vibration over x squared. That if I just restrict my experiments to just one point, then I should get the vibration over x. So the fiber of this vibration over x squared on xx should be the same as the fiber of the vibration over x at the point little x. So that's a nice requirement to ask for our vibrations. And I'm not talking yet about factorization, nor the actual content of locality that the measurements should be independent. But I want to extend already that compatibility that I just gave you for multiple points. Right? So I can perform experiments at n points, not only 2. And that leads naturally to this space, which is called the Runspace of X. The Runspace of X is, as a set, is very simple to describe, is the collection of non-empty subsets, finite subsets of X. So that's a set. And if X has a topology, then Run of X has a natural topology as well. Whenever you have a finite set, a map from a finite set I to X, its image is a finite subset of X. Therefore, it is a point in Run of X. So you have natural maps from X to the Y to Run of X for any finite set I. So you can give Run of X the finest topology, making those maps continuous. You just start adding open sets in Run of X, such that the pre-images under that map is continuous. That means that you're going to consider points. If you have I points in X that are close by, the image in Run of X, they're also going to be close by. So Run of X models what does it mean to be close by for a bunch of points in X, all of them at the same time, n, 3,000, 3 million, whatever it is. But of course, this is, you can have 2 or 3 or 5 points, and they should be compatible somehow. So this is modeled in the following way. Whenever you have a surjection of finite sets from J to I, this determines a diagonal embedding of X to the I, the smallest set, into X to the J, the larger one. In the previous slide, it was the case where I had 1 point and J had 2 points, and that was the diagonal embedding of X into X squared. So that determines a diagonal embedding where several coordinates in X to the J are equal when they are in the same pre-image under the map pi. So in this diagram, what you get is that X to the I sits inside diagonally on X to the J, and of course, the map Run of X is subsets of X. It doesn't care about multiplicities of your points. So this diagram commutes, and you should think of Run of X, therefore, as a union of all of the possible X to the I compatible with diagonal embedding. So this is some sort of a colimit. Unfortunately, for those of you who know about category theory, this is a false statement. The problem here is that the category by which I am indexing this thing is this category of finite sets with surjective maps, and that thing is not filtered. So you cannot take a union under non-filtered sets. It's not sort of like taking the union of vector spaces Vi when I goes to infinity. That's a nice set, the integer numbers. Whether the collection of all finite sets with this thing is not a filtered category, so you cannot really take a colimit. However, you should think of Run of X as a union anyways of all X to the N for every N, compatible with all possible ways of putting inside X to the N inside of X to the M for a larger M by a diagonal embedding. Sorry? What is, I'm sorry, can I hear?
Definition of filter.
Of filter, oh. Yeah, so that, let me just tell it in the form of that are the things that you can take colimits. So if you have 2 maps, there's something that is bigger than both of them. Yeah, I guess that's essentially it. So if you have 2 points, then there's something that is bigger than them, and if you cannot have co-equalizers, are the things that you can take colimits. For example, ordered sets is good. A partially ordered set is something that is filtered, and that's good enough. So this is not partially ordered, because you can put x squared in x cubed in different ways that you cannot compare at all. All right. This is the problem. So I was hinting that we are interested in having these vibrations, so something on x squared, something on x cubed, something on x to the fourth, that I should restrict to diagonals and they should be compatible. But the problem is that therefore that's going to lead to a vibration over the Runspace of X, and the Runspace of X, unfortunately, is contractible. It's a linear space. So this is a theorem in 85. It requires some conditions on X, but these are very mild conditions. And yeah, so it happens to be a space that has no homotopy groups. If you look at just the configurations of points on S1, you see it immediately. 1 point on S1 is just S1, has a non-trivial pi 1. 2 points on S1 is the sphere, is S2. So you've already killed pi 1, but it has pi 2. 3 points on the sphere actually is S3, and so forth. So you kill higher homotopy groups as you take more points on a space, but eventually when you take the limit, you have no homotopy groups. So there are no non-trivial vibrations on run of X. Also, run of X is not algebraic in any way. I want to do algebraic geometry. Not only I want to do vibrations, but I want to do algebraic geometry in this space. And so for those of you who do algebraic geometry, if you look at 2 points on a variety, this is just the variety times the variety, and you divide by the symmetric action that exchanges these 2 points. And that's a nice algebraic variety. Again, the points do not depend on the order. But if you do this for 3 points, this thing is not algebraic in any way. Because now you have 3 points on X, so this is X times X times X. You can divide by the symmetric group action in 3 guys. That's fine. But the problem is that there's these 2 points that are the points X, Y, Y, and X, X, Y, that are the same point in run 3. They are the same subsets that don't care about multiplicity. So this is, if this were an algebraic variety, then you take a point near X. So X sits inside of the run of X. So you take the point X, 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 and you look at a function, an algebraic function, a holomorphic function near that point. That's going to be a Taylor series in 3 variables. That should be invariant by the action of the symmetric group because you don't care about the order of the groups, of the points. And it should satisfy that equality there. And it's an elementary exercise to check that there's no such Taylor function. So this is a good example because algebraic geometers, when you say the configuration of points, of n points in a variety, an algebraic geometer immediately thinks, the Hilbert scheme of points. This is not the run space. This is not the Hilbert scheme of n points. This Hilbert scheme not only remembers the points, it remembers how they collided. The run space does not remember this information, and that's why it's not an algebraic object. But anyways, I want to solve this. I want to deal with this. I want to have vibration, and I want to have algebraic geometry in these spaces. So now let's go to the other notion, the notion of factorization. So I talked about this the vibration of the experiments on X and Y, but I also have my experiments only on Y, and I would also have my experiments only on X. So the notion of locality implies this, that experiments at X and Y are independent, so this vibration over XY, the possible outcomes of performing at the point XY, should be the same as the product of the outcomes at X and the outcomes at Y. And this is a problem. This is something that it seems fairly natural. However, you should be raised in an alarm. Well, this is just a matter of like how you write it mathematically. You have these 2 vibrations, the y square, that was by definition over x squared, or you put y1 and y1 over x and over x. So those 2 vibrations are on the same place. They might be different, but away from the diagonal, they should be the same. So if you restrict both vibrations away from the diagonal, they should be the same. This is the basic property of factorization. And of course, this should smell funny because you have a vibration over x squared, which away from the diagonal looks like the dimension would be the square of the fiber over x. And at the diagonal, it looks like just the dimension at x. And if you know about flat families of any form, the dimension at the spatial fiber always jumps up. It never jumps down. It's an upper semi-continuous function. So there's only two ways of solving this equation, that the dimension of something is equal to the square of the dimension of something, and that's either the dimension is 1, the dimension is probably 3 ways. The dimension is 0, or the dimension is infinity. So for dimensions 0 and 1, you can cook up very trivial examples, but for any non-trivial example of these objects, you're going to have families that are infinite dimensional. So that's the basic property. Since the dimension is going to go down, and I don't want it to go down because I want it to have flat families, then I need the dimension to be infinite. Okay, so before giving you a proper definition of factorization, I want to give you an example, and I want to show that there are non-trivial examples of these things. So this is the notion of the space of principal G bundles on a holomorphic curve. So we're going to take a Riemann surface. I'm going to take a compact Lie group, or think of an algebraic. So think of either SUN or SLNC. And I'm going to be looking at a principal bundle. So these are things that are locally. So at each point, they locally look like you have a neighborhood. This is the disk around the point X. And your bundle restricts to something that is trivial, that is just the product of D times G. And the map from the bundle to the surface is just, in this case, it's just the first projection. So I'm going to be looking at the space of principal G bundles on a Riemann surface. And I'll define the affine Grassmannian this way. This might be an ad hoc definition, but it's going to be the following. This is a very infinite dimensional space. It consists of a principal bundle on the curve. Well, I was calling it X before. Now I'm calling it sigma. For a couple of slides, it's going to be sigma. And a trivialization of that bundle away from the point X. So that means there is this bundle, which is very trivial, on X, on sigma minus X. So that's the trivial bundle. So I'm going to be looking at principal bundles with a chosen isomorphism to this one away from the point X. I'll call that the affine Grassmannian. The Beilinson-Drinfeld Grassmannian is what you obtain over sigma when you let that little point X vary. So this G sub X is the fiber of the Beilinson-Drinfeld Grassmannian over X. So the Beilinson-Drinfeld a point in the Beilinson-Drinfeld Grassmannian is a bundle which is trivialized away from some point of sigma. Now, here's what happens when you have such a thing. So suppose that you give me a point in the Beilinson-Drinfeld Grassmannian. So you have a bundle. You look around a disk around X, and you pick a trivialization of your bundle. You can always trivialize any bundle on the disk near X. So now you have two trivializations. You have a trivialization on D that you chose, and you have a trivialization on the disk minus the point that was the given one. You started with a point in the affine Grassmannian. So by comparing these two trivializations, what you get is a function from the punctured disk to the group. So any point in the affine Grassmannian gives you a function from the punctured disk to the group. And of course, if you change the trivialization, so you choose a different trivialization on the disk, you're getting the same point on the affine Grassmannian, just only changing the trivialization that you chose. So that gives a map from what I call the affine Grassmannian to this quotient. These are functions on the punctured disk to the group, modulo functions on the disk to the group. And what is an impressive theorem of Beauville and Laszlo is that that's an isomorphism. Any bundle that can be trivialized away from a point is obtained this way. So you can start with a bundle on the punctured disk, on the disk, and use the trivialization away from the puncture to extend it trivially to the rest of the curve. And any bundle that can be trivialized away from a point is of this form. So now we have our first example of a factorization space. So you're going to take principal bundles trivialized away from finitely many points on a curve. So that thing there is the fiber over Xn, is fibering by moving the points where you're trivializing away your bundles. And they form a nice factorization space. So I need to prove many things to show you that this is a factorization space. In particular, I need to prove that there is a global space whose fibers are these objects. I'm not going to do that. That's very simple. But the factorization property is the interesting one, and I've already told you the answer. So one way is very simple. I need to show you that if you have two bundles, one trivialized away from X, and the other one is P2 trivialized away from Y, you can obtain one bundle trivialized away from 2 points. And that's very simple, since P1, if you restrict it away from x and y, is already trivial. P2, if you restrict it away from x and y, is already trivial. You can use those trivializations to glue them along the intersection of your curve minus these 2 points. So you glue these 2 bundles and you obtain one global bundle that is trivial away from 2 points. The other way around is the surprising one, and is the result of Boville and Laszlo. So if you have a Riemann surface with a bunch of punctures, with a bunch of points, and you give me a bundle which is trivial away from all of those points, then you can restrict your bundle to the punctured disk, as we did before, and that was the key. The key is that to know a point on the affine Grassmannian, you do not need to know your bundle everywhere in the curve. You only need to know it away from one point, near one point. So that thing gave you this point and this quotient, and now from Boville and Laszlo, you know that to any point in this quotient, you can get a global principal G bundle on the curve sigma trivialized away from x. So you do this at each one of your punctures, and you got now n bundles trivialized away from each one of these points. So that's the factorization property of this space. All right, so now let's define factorization space. A factorization space is going to be a fibration for each x to the I. For each finite set x to the I, you're going to have a space over x to the j. And for each surjection from j to I, that's going to give you a way of decomposing the big space as a product of the smaller ones. And we're going to have exactly the same thing as I did for the case of the diagonal. So you have 2 fibrations, the product of the y over ji's, these are ji's are the preimages of the surjection, over the product of the xji. These 2 things are isomorphic. These 2 fibrations might be different. However, when you restrict them away from the diagonals, these fibrations agree. That's a factorization property. And the space of principal G bundles trivial away from a bunch of points satisfies this property by the theorem of Boville and Laszlo. Okay, so it's not simple to come up with examples of factorization spaces, but it's also not so hard. The key point here was that if you give me a principal G bundle and a point on a surface, you can take out a disk of the surface, transform your principal G bundle locally over the disk, and glue it back, and you get a new bundle. And there are many things that you can do the same way. Algebraic curves, you can re-glue them like this. This is something that sounds silly to an algebraic geometer, but you can take out a disk from a curve, change by a diffeomorphism of that disk, by an automorphism of the puncture disk, and glue it back, and get a different curve. That's false if you do it over C because of completeness, but you can do this in families and get non-trivial families of curves. So you can do this over a base that has an impotence, and you get the moduli space of, you can construct locally a local neighborhood of a moduli space of curves this way. There's many, many examples of factorization spaces that come from the same idea. If you can modify an object locally near a point, you get a factorization space like this. Also, another notion is that from this, and the example of x squared and x, you realize that you can know everything about your space over x squared by knowing it near the diagonal, near the neighborhood of the diagonal. And again, from algebraic geometry, if you have a function that you know is C2 minus the origin, then you know it everywhere. So if the thing that you're missing is codimension at least 2, Hartog's theorem tells you that you can't really do that much. So there are no interesting factorization spaces, algebraic or holomorphic, when x inside of x squared has codimension 2. That means that x has to have dimension at most 1. So if x has dimension 0, that's quantum mechanics and there's nothing to do. If x has dimension 1, that's the content of CFTs or the kind of things that we model. And these factorization spaces only exist when x is a Riemann surface, and that's why the only example that I gave you is a Riemann surface. You need x inside the diagonal inside of x squared to be of codimension 1. All right. So I do representation theory. I don't do any geometry, actually. So I want to connect this to something that is algebraic and in a way that it's that is more linear algebra than algebraic geometry. I should say a couple of words though before. So when I said, I gave you the definition in the previous slide, I told you that yj's are fibrations over xj. Let's fix the categories now. So this x is going to be a Riemann surface. It's going to be an algebraic curve, a smooth algebraic curve. So x to the j is a nice thing of dimension j. But this yj is infinite dimensional. So what does that mean? Well, it's not a scheme, it's not a smooth scheme, but it's a direct limit, it's a union of finite dimensional algebraic varieties, one inside of the other one. They're not smooth, none of them are smooth. In the case that I gave you, which was g of k divided by g of o, so these are Taylor series with coefficients in a group G divided by, Laurent series divided by Taylor series. We have this thing, functions from the puncture disk to modulo functions from the disk to G. When you choose a coordinate, a holomorphic coordinate near a point, this k of x is just simply, let's say that your base field is C, Laurent series on the coordinate. And when you choose a local coordinate near the point x, the ring of functions on the formal disk is just Taylor series on that coordinate. So this quotient means Laurent series with coefficients in G modulo Taylor series with coefficients in G. That was the affine Grassmannian that we had in a couple of slides before. And this thing here is it's not a finite dimensional variety, but it is a direct limit of finite dimensional varieties where you mod out by t to the n here. So you divide by powers of t to the n, take the limit as n goes to infinity. For each n fixed, that's a finite dimensional nice variety, and the limit is an infinite dimensional scheme. An in scheme. All right. So since I want to do linear algebra, and that's what we do, let's suppose that you have such a factorization space as in the previous slide, or as this one, and you have any functor that takes spaces and gives you back vector spaces. And it takes products, and it gives you back tensor product of vector spaces. So in that case, you apply your functor to your factorization space, and what you get is what I will call a factorization algebra, and I want to tell you why it's called an algebra. But in some sense, you want to think of factorization spaces as groups, and these objects as their Lie algebras. This functor gamma can be anything you think of. Chain homology works. Singular homology works. If you have line bundles or if you have sheaves on these spaces, sheaf cohomology with coefficients on those sheaves works. So any functor that you're used to works to take this as gamma. I'm going to take it to be cohomology with coefficients in a sheaf. So I'll do that in a second. But let's keep it to this example. So this example here is the example that I just have in this board. This is the group G of K, Laurent series with coefficients in the group G. And it has a line, it has a central extension. As groups, it's not so nice, but as Lie algebras, it is nice. So this Lie algebra that is a universal central extension of the algebra of Laurent polynomials with coefficients in the Lie algebra G is known as the affine Kac-Moody Lie algebra. This central extension is split over G of O. So if you see as G of O, that central extension is split. So notice that we have some extension of this guy, this G hat. So if I restrict this G hat over G of O, well, I can think of this G hat over G of O over G of K over G of O. So I'm just dividing that extension there over G of O. And what I get is that this thing here is a line bundle over this. And indeed, so that line bundle, I'll call it L. It's a line bundle over the affine Grassmannian. This was the affine Grassmannian. For any point x, once I choose coordinates, all of the affine Grassmannian look like this. The isomorphism with this depends on the choice of coordinates, of course. I can change my coordinates. I'm going to get a different isomorphism. But I have this line bundle to play with. And the functor that I'm going to take is going to be take cohomologies of that line bundle. Now, you shouldn't be surprised of something. Like, this is a group. Maps of anything into a group is a group. So that group, which is the loop group of G, acts on this variety, or on this infinite dimensional object. It acts by multiplication here. So G of K acts by multiplication here. And this thing is also a group. So G hat also acts here. So it's not surprising that so if I have this variety that you should think as the affine as a Grassmannian or as a flat variety, if you wish, with an action of the group, which is this group, if you take a line bundle, which is this line bundle, and I take cohomologies of that line bundle, then that's going to be a vector space where this group is going to act. So it's not surprising that this is interesting for a representation theorist. representations of the affine Kac-Moody algebra are going to appear by taking cohomologies of these line bundles. Indeed, this is just the level k representation of the affine Kac-Moody algebra when you take the kth power of that line bundle. So if you know what the affine Kac-Moody algebra is, this is a nice way of constructing the highest weight representation, integrable representation of the affine Kac-Moody algebra. Okay. All right, so now why am I calling those things factorization algebras? And now it starts to become more and more abstract. So up to now, I think it was more or less examples, but now it's going to be abstract. So I said that I wanted to do algebraic geometry on the Runspace of X. But unfortunately, Runspace of X is not, it's contractible. It's not interesting as a topological space. But if I view it as the limit of x to the n, then I can think of a way of writing what sheaves on that run of x is. So the idea is the following. I don't know how to treat this guy as an algebraic object because it's not. But I do know how to treat these guys as an algebraic object because I do know this is a nice algebraic variety. It's the power of a curve. So if I had something that I wanted to call here a sheaf, let's say that I have some sheaf, something that I would want to call a quasi-coherent sheaves on the Runspace of X. And of course, this category doesn't really make sense yet because it's not an algebraic object. But this map, I declared it to be nice. So if I had such a thing, I would have this thing, which is the pullback under pi of this f. And if this wasn't reasonable in any way, this would be a quasi-coherent sheaf or a nice sheaf on x to the I. So now, moreover, I will have something for x to the j as well. So I will have my fj, also a quasi-coherent sheaf here. And remember that I have a diagonal map like this whenever you give me a surjection from j to I. So what I will define as a quasi-coherent sheaf on run of x, I'll forget about this object itself, but I'll just remember all of them and their compatibilities. So a collection of sheaves fi, each one on x to the I, compatible with these diagonal morphisms, meaning that the pullback of fj under the diagonal map is the fi. That thing, I would say, it's a sheaf here. And that's a nice category that has all of the properties of the quasi-coherent sheaf category, which is now on an infinite dimensional space. Okay, so that's more or less what is written in this slide. I'm going to start with this family of quasi-coherent sheaves on x to the I. And this slide only remembers what does it mean, what do I have on x and on x squared. Okay? Having a family everywhere, in particular, will give me the case where I has 1 point and j has 2 points, and the unique diagonal is the diagonal of x into x squared. And I already there see something very interesting. That the compatibility conditions are these two. The restriction of the 1 of x squared to the diagonal should be f1, and the restriction away from the diagonal of f1 times f1 is f2. So by collecting these two things, you get a multiplication on f1 for free. So let's say that, how does this work? You have x squared. So we have x, and we have f1 as a sheaf on x, f1 as a sheaf on x. You pull them back by the first and second projection. Now you have these two sheaves on x times x. You take the tensor product there. That's this box product f1 times f1. Running out of time before even close where I have to do. Okay, so you give me a section of f1. You give me another section of f1. Now you have a section of this thing that you want to multiply. You restrict this away from the diagonal. So that's a section on this j is x squared minus the diagonal inside of x squared. So you restrict this section that you had of f1 cross f1 away from the diagonal. This thing is isomorphic to f2. That's the factorization property. So now you have a section of f2 away from the diagonal. That section of f2 extends uniquely to a section of f2 on all of x squared. You extend it across the diagonal. And now that gives you, by restricting that section of F2 to the diagonal back, you get a section of F1. That's the multiplication. And that's why when you start with anything that factorizes, you get a multiplication on your sheaf on X. So you get an algebra structure. OK, so this is just another way of saying what I already wrote in this slide. So I'm going to, on the board, so I'm going to pass it quickly. The idea here is that there's an easy way of writing sheaves on the run of X by starting from a sheaf on X. You just give me something that is supported on the image of X inside of run of X. So for each X to the I, you just define it to be the push forward on the diagonal. That's a nice sheaf on the run space of X. OK, good. So we're getting to where I want to. The run of X, remember, this was finite subsets of X. Has a nice group structure. Well, almost a group structure. It has a nice semi-group structure. You can take the union of two finite sets, and you're a finite set. Whenever you have a space with an associative operation, this is an associative operation, taking the union of sets, and compact fibers, these are finite sets. So if you have any set, any finite set on X, you can only express it as a union of two sets in a finite number of ways. So the fiber is compact. Then you can just take functions and take the convolution product. So if you have a function of run of X and another function of run of X, you pull them both back to the product of run of X times run of X, you multiply them there, and then you push them forward to run of X. You integrate them because the fiber is compact. So that you can do for functions, and that you can do for sheaves. If you do this for sheaves, you get the notion of a tensor product on the category of sheaves. And this is something very simple that is expressed here. If you have two sheaves on run of X, you obtain a tensor product by this convolution product, the fiber of which at the finite set R is, well, the same as the convolution of functions. You write R as a disjoint union of sets, S and T, and you just take the fiber of one times the fiber of the other one, and you multiply. So that's a nice tensor structure on the category of sheaves on the run space of X. It's compatible with the operation that the run space of X has. But once you have a category of sheaves, I just told you what quasi-coherent sheaves are, and you have a nice tensor product on that category, you can do algebra there. So you can ask, what is a Lie algebra on that thing? What is a commutative algebra on that thing? And a Lie algebra is exactly what a factorization space gives you. What the linear version of factorization space is a Lie algebra for that tensor product. So that's an example of how it works, how the tensor product works. So let's take two sheaves on X. So the tensor product will not have anything on X. And this is because you cannot decompose a set of one element into two disjoint sets. But it will have something in X squared. It's going to start having something on X squared, and it's that. This is the way of decomposing a set with two elements. You have two ways. You put X and Y or Y and X. And these are the two summands in my definition of the tensor product. The J, the restriction away from the diagonal comes from the fact that I was taking disjoint union of sets instead of just union. A Lie algebra for that tensor product, therefore, is a map from the wedge product of F with F, it has to be skew symmetric, to F. The action of the symmetric group exchanges F and G here. So instead of taking two summands, you're going to get only one of those summands. So here I've already modded out by the action of the symmetric group in two elements. Any map like this is skew symmetric. Why do I have this push forward here along the diagonal? Well, this is again because the sheaf associated to F on the run of S is just a collection of sheaves. On X, I have something which is F. On X squared, I have something which is the push forward along the diagonal of F. And that's this, that's this guy that appears there. On X cubed, I'm going to have the push forward along the diagonal of X into X cubed of F, and the tensor product is going to have more components. And I'm going to have more maps. But the very first map that you get is this map. And if you remember a few slides ago, this is exactly the map that the affine Kac-Moody algebra gave me. So the upshot is that if you start with a factorization space and you take line bundles over them, as the affine Kac-Moody algebra case, you take cohomologies of those, you get one of these. You get a Lie algebra. Once you have a Lie algebra, you can define the cohomology of that Lie algebra. This is just abstract nonsense. If you have a Lie algebra, you have the Chevalier-Eilenberg complex. I promise I'm finishing in a couple of minutes, but this is the last slide anyways. I just want to state at least a theorem. And this, the cohomology of this complex is what's known as chiral homology. This has had tremendous impact in the theory of conformal field theories, vertex algebras, and so forth, starting from the work of Zhu, 1996, where he proved that if you start with any of these objects, I just gave you one example, which is the Affine-Kac-Moody one, and you looked at it in the case when X is an elliptic curve, then the zeroth cohomology of that Lie algebra that we just constructed is finite dimensional. It's generated by the irreducible modules of your algebra, which are finitely many of them. And moreover, it changes nicely when you move X in the moduli space of curves. In particular, it gives you a vector-valued representation of the modular group. So this is the statement that you may know, that if you have an Affine-Kac-Moody algebra and you look at the representation, you look at all the characters of the irreducible modules, those things are invariant they're convergent, the traces, the characters are convergent, are invariant by the modular group. But this holds for any algebra. So Beilinson and Drinfeld asked the following question, whether or not this higher cohomology vanish, in this case, for an arbitrary curve and an arbitrary level for an Affine-Kac-Moody algebra. This is an unwritten, unpublished theorem of Gaitsky for any curve. This is a theorem of ours with Jethro for SL2 at arbitrary level over elliptic curves only. And lately, last year, Bailing, Song, and Andrew Linshaw published a paper that, they solved a linear algebra question that we asked that would reduce the problem to computing the vanishing of this cohomology in the other ADE type cases. So let me just tell you quickly what is the technique to proving this theorem. Otherwise, it's absolutely all content free. So to prove the vanishing of this theorem, what you do is, I want to prove that this cohomology vanished, but this cohomology depends on X, and X is an elliptic curve. So what you do is you prove that this thing varies smoothly when X moves in the moduli space of elliptic curves. You go to the boundary of that moduli space. That's the elliptic curve that is nodal. You understand what happens at the nodal level, and you prove there is zero. And, so that's the technique that we used to prove the vanishing of this. There's absolutely nothing known about these cohomologies away from degree 0. In degree 0, this has the name of conformal blocks. In higher degrees, no one knows absolutely anything except these cases and similar cases for the Virasoro-Lie algebra. So any result on this topic is interesting. This topic was designed by Beilinson and Drinfeld in '96 because they phrased the whole geometric Langlands conjecture into a non-vanishing of these cohomologies for a particular algebra. So if you prove that for one particular algebra called the chiral Hecke algebra, this cohomology does not vanish in 1 degree, then you prove the geometric Langlands conjecture. All right, so I'll just stop right there. I think I'm just in time.
Okay, are there questions for Reimundo? I have a short question. Isn't there, I seem to remember there is some kind of operatic viewpoint to this factorization?
Yeah, so, right. So you can look at the configurations of points on a surface is an operad itself. So you have this little disk operad on a surface. So if you take that point of view, so if you look at algebras for that operad, they are baby versions of these objects. If you take, in principle, if you take DG algebras for that operad, they should be the same thing as this. And the only problem is that there you're using not an algebraic topology, you're using just the usual topology. There's the whole school of people like, I guess names attached to that would be Kevin Costello, probably Jacob Lurie before. So if you take that approach, then you have this whole theory of factorization algebras in that topology, You have Beilinson-Drinfield's theory of factorization algebras in the algebraic setting. Beilinson and Drinfield's have this theorem that says any vertex algebra, which is something that we understand from representation theory, gives rise to one of these. So it's easy to construct examples of Beilinson and Drinfield's kind of factorization algebras coming from representation theory. And there's no known way of proving a connection between the smooth setting and the algebraic setting. So it's very hard to construct examples of the other cases. That's a very active topic. People are trying to construct examples on the other side, and they match up to what we know on the algebraic side, but they're very limited.
Any other question?
So what happens if you consider some kind of compactification of the space of configuration of points instead of Randex, like Fulton-McPherson compactification?
Yeah, okay, that's a very good question.
Because in that case, you have a good space to work.
Yeah, I don't know how to give you an answer to that question. So I can tell you people that tried to do something, and no, let me postpone the answer to that. So what happens is the following. So there are everything that we know for vibrations of a run of X. Okay, so the Fulton-McPherson compactification is something that depends a lot on what X is. So when you start with X, you get completely different compactifications depending on what X is. The problem of that is that all of the examples that we know how to construct are of the form like this one. This one didn't care at all what the curve X was. The important thing here is that this guy has an action of the automorphism group of this thing, which is the local ring at a point on a curve. So that is what allows us to move this space from X to a little x to the whole curve. So all of the examples that I know how to construct of factorization algebras like this come from this form. It's something that I know how to put on top of one point on a curve and then spread it up on the curve, and this exists on any curve. So it's a CFTs of the form that I give you this object. It's the vertex algebra, which is the Affan-Kac-Moody vertex algebra. This exists independent of a curve. Now you give me a curve, and I can paint that curve with these CFTs. To construct a non-trivial example on what you're suggesting is something that only depends on X itself, and it does not live on any other curve, and I am not aware of CFTs of that form. So that's the most honest answer that I can give you.
Okay, thanks.
Any other question? If not, let's thank Reimundo again.